Alright, so today we're going to be talking about the calculus of parametric functions. And the good part is there's not many new tools that we need to know outside of regular calculus. Alright, so let's start with the derivative. So we know that a parametricized curve is when we have a function that defines y and a function that defines x, and both of these functions are functions of t, so we have some common variable that define x and y, and we can sort of combine these x's and y's at a specific point, at a specific t value, and in that sense we can kind of get an x comma y pair. And so all we're doing is we have some function that relates x and y, but instead of y being directly related by x, we have a function t that describes the behavior between x and y. So that's what a parametricized, or that's what a parametric function is. And so a parametric curve having these two relationships has a derivative, at some t value, which is t naught, if f and g have derivatives at t is equal to t0. So all we're saying is that our parametric function at some point t0 has a derivative if both this equation and the equation that describes y both have a derivative at that point. And so a curve is differentiable if it is differentiable at every parameter value and smooth. So these two terms are what I'm defining what differentiable means, and smooth if f prime and g prime are continuous and not simultaneously zero. So basically, we can call our parametric curve differentiable if for every value that it takes on, we can differentiate it. So dy over dx is defined at every value. And it's smooth if these functions, the derivative functions f and g, are both, and then this is g, actually g of t, if these derivative functions are both continuous and not simultaneously zero. So that was some of these definitions. And so let's just use an example. So if you have x is equal to cosine t and y is equal to sine t, we're worried about the interval between the interval between 0 and 2 pi for t. Then we know that x prime in this case with respect to t is simply minus cosine t, and then y prime is simply cosine of t. And since these two functions are continuous on the entire t, then we know that and they're not ever zero at the same time. We know that the derivative or the curve is smooth, and we can say that the function is differentiable because at every parameter value for t, we have a corresponding derivative definition. So smooth curve and differentiable. So that was just applying the definitions that we saw earlier. And this should be a U, not a E. Alright, so that was the definitions. And so far we have just differentiated with respect to t, but what if we were asked to find dy over dx, right? And so we have y is some function g of t, and we have x is some function f of t. And we can easily find dy over dt and dx over dt, but how do we sort of reason about dy over dt, which we're used to? And if we sort of apply the property of derivatives, we know that dy over dx and we saw this in the chain rule, if we can get dy over dt and multiply it by dt over dx, that can give us dy over dx. And we know that dt over dx is simply 1 over dx over dt. This comes from just the properties of derivatives. And so given all these facts, we can write dy over dx as dy over dt divided by dx over dt. And we already know how to find each of these components by simply just differentiating the given values that we have from our parametric function. And so essentially, if I use this example, then we get dy over dx is simply equal to y prime divided by x prime, where we're differentiating each of those functions with respect to t. Now, what about, so that was how we find dy over dx, and that really just came through like the application of chain rule, and which shouldn't be much of a surprise since parametric equations are just defining a function with respect to a variable t instead of directly making a y and x relationship. Now, what if we want to find the second derivative, d squared y over dx squared? Notice how we can further apply chain, like d squared y over dx squared is simply dx of dy over dx. But likely when we get this dy over dx equation, since it's the quotient of two functions or two derivatives that are both functions of t, what we'll get is this dy over dx will be defined in terms of t. In terms of t. So we cannot directly differentiate it with respect to x. So we need to find another sort of way to represent d squared y over dx squared. And essentially, we just apply the chain rule again. We know that whatever function we have over here, if let's just call it like dy over dx, call dy over dx is equal to some function y prime. And this is different from these y primes that I had earlier. This is y prime is that function, the derivative, the first derivative of our parametric equation. So we have that. And now, like, we know that if we just want to differentiate this with respect to x, we can simply do dy prime over dt times dt divided by dx. And we saw this earlier as just 1 over dx over dt. And so d squared y over dx squared is simply equal to dy prime over dt divided by dx over dt. And so the chain rule again allowed us to come up with an identity to form the second derivative of this function. You can find out higher order derivatives in a very similar manner. So once we have the first derivative of a parametric equation, we simply differentiate that first derivative with respect to t, and then we just divide it by this derivative of x with respect to t, which we should already have if we calculated the first derivative. So let's practice with this. Let's find d squared y over dx squared for x is equal to t minus t squared and y is equal to t minus t cubed. And so the first thing we need to do is find dy over dx, and we know that dx over dt is simply equal to 1 minus 2t, and dy over dt is simply equal to 1 minus 3t squared. And from what we derived earlier, dy over dx is simply equal to 1 minus 3t squared divided by 1 minus 2t. To find dy squared over dx squared, we need to differentiate this with respect to t and then simply divide by this equation. And this should be t, looks like next. Okay. So let's use the quotient rule to differentiate this with respect to t. So d over dt of 1 minus 3t squared divided by 1 minus 2t is simply equal to minus 6t times 1 minus 2t minus 1 minus 3t squared times minus 2 divided by 1 minus 2t squared. simplifying all our terms, I get minus 6t plus 12t squared, and then minus 2, and then minus, so plus 2, plus 6t squared minus, so minus 6t squared, which simplifies to 6t squared minus 6t plus 2 divided by 1 minus 2t squared, and then I simply divide it by this equation over here, so that will give me d squared y over dx squared, and that will simply be 6t minus 6t squared minus 6t plus 2 divided by 1 minus 2t, and then cubed now. So that was what the original problem asked for. So it's just using chain rules. So again, not much different from what we have seen so far, but it's just parametric forms or something, or calculus of parametric functions is not something we have explicitly dealt with. So one application of parametric functions is finding the length of a curve. And this curve, we know how to do this with non-parametric functions, but what about a parametric function? So if we have x is equal to some f of t, and then y is equal to some g of t. So in this case, if you want to find length of curve defined by f and g between a and b, where a and b are 2 points, then our length is simply equal to the integral from a to b of the square root of dx over dt squared plus dy over dt squared. I'm not going to go over the derivation of this, but if you remember how we derived the length of a regular non-parametricized curve, the derivation kind of follows similarly, but if you want me to derive it, let me know. I can derive it in another video. So given this equation, let's use it to find the length of a curve. So let's say that we're given a function x is equal to cosine cube t and y is equal to sine cube t. We want to find the length between t is less than or equal to 2 pi and t is less than or equal to 0. So essentially, what we have to do over here is, and we're given that this parametric function creates a curve that looks sort of like this, sort of like a ninja star, where if I can draw this better, so we have, and on all quadrants, the shape of the curve is similar, so it looks like a ninja star. And to go from one quadrant to the other, this is when t is equal to 0, and this is when t is equal to pi over 2. So given that part, that all of these, the shape of the curve is symmetric on all 4 quadrants, we essentially just need to integrate on one quadrant, and that should give us the length properly, right? So that's a technique we're going to be using. And so another thing we have to do is we have to find dx over dt, which is simply equal to 3 cosine t squared, and then we have to derive cosine t, so that's just minus sine t, and then dy over dt is equal to 3, oops, I messed up, not 3 cosine t squared, this is well, oh wait, I was right. 3 cosine squared t, and then minus sine t. And then dy over dt is simply equal to 3 sine squared t times cosine t. And essentially what we're finding the integral of is then just the integral. So the length is equal to, or 1/4 of the length is equal to the integral from 0 to pi over 2 of the square root of this thing squared, which is 9 cosine to the power 4 t sine squared t plus 9 sine to the power 4t cosine squared t. So that's what we're trying to find the integral of. One thing we can do over here is we can take in common cosine squared t and sine squared t. So we can simplify this to 1 over 4 L 0 to pi over 2 and then 3 I removed times the square root of cosine squared t sine squared t times cosine squared t plus sine squared t. Now this part through the trigonometric identities is just 1, and so essentially our integral simplifies to the integral from 0 to pi over 2 of 3, and then I'm gonna remove the square root, so 3 times the absolute value of cosine t sine t. And the good part is, since our domain is only from 0 to pi over 2, we can also remove the absolute value signs over here, since the product of, well, since every trigonometric function is positive in the first quadrant, this product will also be positive. And that was one good part about just looking at the symmetric domain. So we have that. Oh, and then forgetting the dt. Now the question is, how do we simplify this? We use a u substitution, so I'm gonna do w is equal to sine t as my substitution, and then I get dw is equal to cosine t dt, and so I get 3 times the integral from 0 to pi over 2, and this is in terms of in terms of t, not w, of w dw, and then this is simply w squared divided by 2, which is simply equal to sine squared t divided by 2 from 0 to pi over 2, and then don't forget to multiply the 3. At pi over 2, this is 1, so we get 3 over 2, and then at 0, sine is simply 0, so our answer is 3 over 2 times 4. And then, so if I multiply this by 4, I get 6. So that's the length of the curve defined by the parametric equation. So that was like an application of integrals with parametric equations. So hopefully this, along with me covering how to find the derivatives, helps deal with calculus and parametric functions.